So I'm Ralf Staudemeyer. I'm a researcher, lecturer, author, globetrotter. So I traveled a lot in the last 20 years being an academic. The last 2 years I did support a EU research project on security and privacy in smart cities as a scientific and technical coordinator. And that's how I came to sort of that field. Like, remembers me 4 years ago, I held a presentation on Android security, so this is now completely different. My research areas are security, privacy, IoT. I do a lot of networking, mobile computing, and I actually come, concerning my PhD, from artificial intelligence. So, I lecture at the University of Passau, in Passau, meaning network science, which is sort of related to graph theory, and I do IT security at the Schmalkalden University of Applied Science. I have some hands-on experience working with networks and building networks. That was the Forschungsverbund, and I'm author of the Langfristige Signal Monitoring Cookbook. I wrote this 5 years ago. So my academic work was mainly in South Africa and Fiji Islands. I lectured there a couple of years, and currently I'm located in Germany. So concerning the Railroad project, so that was a EU project related to security and privacy in smart cities, and the context was sort of, okay, if you would like to fix smart cities, we need to look at IoT, and the European Union is really interested to get these kind of things sort of not wrong, absolutely wrong. So, but sort of the conclusion, I already take this at this point, that IoT in smart cities is not really fixable. So that's my conclusion after running the project. So Railroad was about reliably smart and secure Internet of Things for smart cities. Developed IoT-based architecture framework to provide smart city services. And whole focus was on security and privacy by design. We had use cases related to smart home environments and smart cities, so mainly smart transportation and environmental monitoring. So the project was run for a few years. We had €5 million to spend, which we actually did. A couple of industrial partners, including Siemens and Atos, and a couple of universities in there. So we built a low-power IoT device together with the company Solötier, who was also part of that consortium. Our first ideas was actually consider something so the question was how much hardware, like how much memory, how much computing resources do we actually need in IoT to implement security. So first we took basically the chips which are in smart meters as reference, which are built by Texas Instruments, and they have about 9 kilobyte RAM to work with. To put this, it's not possible. With 9 kilobyte RAM, we cannot implement any security, even if it's in the chipset, which is in that case, but end-to-end security is not really feasible with it. So in the project, we fixed end-to-end security with DTLS on the remote. On the remotes, we had Contiki running, and we implemented that on the remote, implemented confidentiality, integrity for communication, and origin authentication with asymmetric keys, and it works. Like first tries, for example, to generate keys at the beginning, it took 15 hours. We ended with something fearful. So actually operations like signatures go in less than 2 seconds. So ECDSA, ecliptic curve cryptography was, like said before, that it's not really feasible to get this running on things. We got it running. OK currently uses the NIST curve, which is sort of problematic, but AdWords should be possible as well. We developed GSS, which is a container format for JSON data actually to transport signed values over into infrastructure. With this, we had end-to-end integrity protection in there and origin certification, authentication as well. So these are basically most of the basic building blocks to have security implemented in the IoT. So, but what is now the context about smart cities? So smart cities, I will not go really in detail what smart cities are. We can expect they will come. There's a lot of investments from many municipalities actually to get smart city services to address environmental pollution, waste management, municipality management, public safety, maybe cameras and that stuff, energy supply, smart grid, traffic management, like to reduce pollution in certain areas, and public transport. There are tons of services that go into that direction. And the opportunities that come with smart cities is basically to provide intelligent and smart solutions and put this on ICT-based services and provide them to the citizens and actually make cities attractive in that regard and improve general quality of life. Smart cities can be used as a driving force for economic growth. That was sort of the aim why funding is pressed in these kind of projects. So now the dependencies are, we need some sort of technology foundations that enables the interconnectivity between, first between different activities of life, and on the other hand, between various devices and services. So then we need sufficient information and data from different aspects, so health, transport, governance, and we can sort of try to combine the data to generate new services. And we need some sort of infrastructure to provide smart applications, for example, app running on a smartphone or some sort of devices which can be used somewhere, so that enable human-computer or human-service interaction. And we need to really basically involve all relevant stakeholders, which are the municipalities, which are service providers, citizens, or basic companies who would like to provide a service. So, but now, what's the cybercrime part on this? So, smart city and cybercrime. So, we have a rapid deployment of ICT infrastructure, we have extensive digitization of available information, and we have a key technology which is based on Internet of Things, IoT. IoT enables to connect and communicate with a vast amount of smart city things, which we have distributed everywhere. Things collect, process, share, and distribute critical information. So the goal is for municipalities to manage a whole city efficiently and effectively. So now we come down to Internet of Things. Enable things to connect anytime, at any place, with anything, ideally using any path, network, or service. So what relates to this? First, things need to make themselves recognizable. Then they need to sort of make context-related decisions. They need to be able to communicate with each other and with the infrastructure. They need to be able to access information aggregated in other things to interact with them and to make context-related decisions. And they need to be components, or are components of complex services which are not necessarily imagined in the time the device was built. So, but doesn't IoT have some sort of serious security and privacy issues? Yes, sort of. Let's take a look. So, we have data protection issues. So, users do not have control over collected data. They have no clue what happens with the data in the device, where the data gets stored, where it's distributed. Not really an opportunity there. So there's no option to verify. So the user doesn't know if the agreement with some service provider related to the device actually is doing what the users expect to do. In terms of service provided or in terms of data which is leaking. There's no option to gain control because there's no human interface to that device. It's a tiny device. If you have it, like if it can be in a shoe, it can be somewhere, you can lose it. It might be in your couch for 10 years and you have no idea. So then it leaks data to the cloud. For example, medical data. The data collection sparks interest, concerning businesses or attackers, like getting access to the information to exploit that information. And the question is always, if data gets lost, who's responsible? The person who owns the device, the maintenance service, the manufacturer. For example, if I have some sort of human, like a digital assistant at home, and I run a party, and that assistant collects information about the people there, like voice profile or whatever, and someone doesn't want this, but the data is already at Google or Apple and processed there, who is responsible for that data or a personal data breach of that certain person? Things like this are still unclear or are in the process to be regulated. So, but who looks over that? For example, if we have a Chinese company or for some company from some other countries, it's still like sort of unsure how this will evolve over time. We have other security issues. For example, time to market beats security. So if a company, if a startup develops some IoT device and they need to push it on the market as quickly as possible, they will not care about security. And that company might be there for 2 years, then support might end after 1 year, but the device runs 15 years. So it's like there is no provision or no perspective that this kind of that these security issues related to that can be sort of addressed. There's no budget for security, especially for small companies or for very, very cheap devices. There's no user interface to make security adjustments. It's just very difficult to implement. Then you always need to consider that even in a secure infrastructure or in an infrastructure you consider private, that one hacked device is sufficient to forfeit security in a whole internal network. So if you have a house with hundreds of different devices in there, even if you have a separate network infrastructure in there, it doesn't really mean that it's safe. There could be one device which basically breaches all security for your internal infrastructure. Then device lifespan is always will always be beyond the support period. Then many manufacturers do not have any expertise in security, and because they don't come from the security area, they may be good in building light bulbs and not building smart lamps. And you have things like you have an intelligent door lock you can open remotely, but what about if the service provider doesn't exist anymore, if you have no internet, if other people can open your door lock, or if your battery is empty? So things like this are not really solved yet. So we have safety and reliability issues. We have medical equipment, door locks, heating, cooling, all these things, or maybe industrial control systems running trains. The failure might always be fatal, and we're not at that point there where attacks really cause us the damage necessary actually to trigger a change. So what about driving cars? We know that that cars are hackable. Things like cars we built today. I didn't see the presentation now, but I assumed it looks at similar things. So who's responsible? What happens if things go wrong on a large scale? The no internet, no service problem, the empty battery problem. What about cloud-like services or devices that depend on cloud services? Does the device work if the cloud doesn't exist anymore? Definitely not. So what if manufacturers are bankrupt, render devices useless, and the whole interoperability thing is also not solved. We have own clouds, own applications, and yeah. So then we have support issues. Support costs money, doesn't generate revenue. There's little profit. Imagine that motivate quality, and end users can fix. Now the question is if end users can fix issues themselves. The problem is hard to motivate. We have intellectual property issues, and in general the manufacturers are not really interested that users fiddle around with their systems. And a short lifetime, especially in the IoT world, is pretty good for business, so which is also a problem. Market conditions. So enforcing insecure systems, like for example with smart meters, sort of like part of the market infrastructure is a little bit, or my impression. Then we have starting to get fewer and fewer devices without smart or cloud. Try to buy a TV which is not smart and not cloud, not with a camera inside. It might get difficult over time. So we have closed systems instead of standards, and we have no security and privacy enforced, and the whole certification models, which try to improve this, focus on the business models and on the customers. So what does it take for a smart city to be safe and secure for its inhabitants and respect their privacy? So also was one of the key questions, and I put that LOL for laugh out loud because it's not really fixable. So let's put some meat behind that. So information security basics in IoT. So we have the security management, the risk assessment related, most of the related to certification. We have software and operating system security, where we know the vendors that do not have the resources. We have middleware and trusted systems. Trusted systems is sort of broken at the moment because there's not really trusted infrastructure, or it's hard to put that in infrastructure. We have on-device security and trusted hardware. Trusted hardware also doesn't really work. We did some measurements on security chips, where we figured out that actually there are other operations concerning energy usage on encryption and verification operations, and at least in the experiments we've done, we came to the impression there are other activities in there as well. So I would not trust hardware as well. So then we have the traditional security challenges in the IoT, which are sort of fault tolerance and fail-safe behavior. So if things go down, if devices go down, services or infrastructure shouldn't go down. We have infrastructure integration, monitoring, updates. We have efficient cryptography and key management, which needs to be addressed, where the key management part is the most difficult. And we have ownership, who owns things, and we have secure collaboration. And finally, we have privacy, trust, and data minimization, which are at the moment not really addressed in the IoT. The true challenge is large-scale deployment with sensitive data. So the information security goals related to the IoT security challenge. The traditional challenges are the CIA, so confidentiality, integrity, availability. So the first two we actually fixed. Availability is a huge issue and remains. Then we have authentication, authorization, accountability that sort of can be addressed. And we have end-to-end and hop-to-hop protection, which needs to be ideally nested, but is pretty resource intensive, but sort of can be done. So I would skip a couple of slides now. So in Confident in the IoT, we basically implemented this. It works now with DTLS. It can be nested, so we know it's possible. In the smart city context, we have the smart meter example with a frequent measurements. A lot of profiling can be done. So in theory, if we would have a little bit more resources on the smart meters, we could reduce information leakage on these devices. So integrity and veracity is about like changing information. We implemented signatures, so that works as well. So it basically ensures that values cannot be changed on the way, and that we can make sure that actually values come from a specific device. So that also in a smart city context, here we have the example of environment monitoring. Part of the REROM project was the city of Tarragona in Spain. So they have pretty old, it's quite an old small town around. They have a lot of chemistry factories, and the question is, they expect that sometime they will have some environmental problems where the city needs to be evacuated because some factory goes up, or there are other kind of air pollutions. So they try to implement sensors around the city. So this was part of the railroad project and successfully done. And now, obviously, if you have evacuation, such kind of infrastructure attacked from the outside, and evacuation triggered, and you do this 2 or 3 times without any reason, that kind of infrastructure will not work anymore because people just will not react to such an alarm. Here we have another example. So, for example, faulty air pollution sensors, which can declare city areas for zero emission zones. That basically they block these areas for traffic, and if you can trigger this, you can create also difficult congested road conditions on purpose in the city. So, private communication, that was one part we left off. Smart city-wide area networks are impossible to physically secure access against unauthorized access. Irrespective from successful use of modern cryptographic techniques, attackers may eavesdrop communication and analyze network traffic. So we have proxies, we have VPNs and dummy traffic. We have some options for anonymity, like mixed networks and onion routing, which just works on a large scale. You can do this with big networks, but not with small sensor networks. And we have unobservability, which basically we have broadcast option and DC networks. Who knows what a DC network is? It comes from the Dynamic Cryptographers Network. I published a paper on this 6 months ago at the CAMAT conference, where we implemented on an IoT device a protocol where the sensors can send each other sensor values where wiretapping doesn't help. So basically, it's impossible to say for someone who wiretaps the communication between the devices if there was something communicated or not. And it's cryptographically not breakable. Basically, it's possible to say there is communication between the devices, but it's not possible who communicated which values to the other contributors of the network. The problem is with these kind of communication protocols, they do not scale. If you send 1 bit to 6 nodes, it takes you 1,000 bits basically to communicate. But it's sort of, it gives some security for sensitive environments where wiretapping cannot be excluded. The idea comes from David Schaum, who wants to look into that. So, linking protocol data, like metadata, who knows the Skype example? In 2007, Skype was still an owned company, not owned by Microsoft. The crypto protocol was not clear at that time. So the Swiss military tried to figure a way to extract communication information out of recorded traffic, which was recording was always really difficult because the communication was sort of distributed in the network infrastructure. There was nodes and supernodes were forwarding traffic. So they had small snapshots of communication. The task was to decipher without knowing anything, without really cracking security. So they did this via frequency analysis, and were able to extract what was communicated between the source of where like a probability of 80% per word. So if a human would look over it, would have a pretty good clue what was communicated. And this is also similar problems you get in this kind of infrastructure by how much was communicated and how much information is this. A lot of can be extracted by that. So we need to counter traffic analysis, which makes things really, really harsh. And sort of the aim must be to make node activity sort of unnoticeable. So IoT-based smart city services, which is basically everything smart. We have environmental monitoring, waste and water management, energy metering, traffic management, parking, public transport, structural monitoring, street lighting, and all these things. You can pick them. We were able basically to find attack vectors which were already used or which are obviously already broken because there are publications who explain how this can be done. So the threat landscape of smart city services are blend of existing physical entities of the private and public space with digital technology. There's no clear boundary anymore between physical and the digital part, and these systems are deeply integrated and interconnected into some cyber-physical systems, which makes it a very complex threat landscape. So there is no, by mixing the virtual and physical world, there's missing something which we can define as a ground truth. So if we have a separation between the real world and the cyber world, we can still assume that things sort of stay in their own entity. But if there's an interaction between physical and the real world, things sort of get difficult for humans. Manifestation of malicious interventions in the physical realm itself. So we do something in the virtual world, get direct effect in the physical world. So now I have a couple of real-world incidents which I found interesting. In 2013, Iranian hackers breached remotely a water dam outside New York. The attack did not cause damage, but demonstrates remote control of physical infrastructure. In December 2015, the Ukrainian power companies experienced unscheduled power outages affecting 230,000 households. So, first confirmed, this is the first confirmed hack to take down a power grid. Well-prepared attack spanning long preparation time. It was linked to Black Energy 3. Who knows Black Energy? Yeah, okay. So then we have both in April 2016, that's a nuclear power plant in Germany that was infected with malware that provides remote access. The threat was considered low as the systems were isolated from the internet, but they found 18 removable media drive which were infected. So 1 year later, this is about the Dallas storm warning systems. So there were 156 different alarm systems which started blaring across the city around midnight. It took 90 minutes to silence them by shutting down their radio system. Malicious actor penetrated the radio system and initiated the alarm. So then we have WannaCry. I think that was sort of the biggest attack we had this year, and sort of affected a lot of different services. So, I don't know, I think it's sort of the biggest attack we had in that regard, and I think we have to expect more. So it included hospitals in Germany, electronic boards displaying train route information were disrupted. Renault stopped production of cars. So the FedEx services in the US. So hospitals were affected in a couple of countries. So airlines, airline operators, telephone operators were affected. So sort of that had a worldwide scale. So one major issue is that numerous IoT systems share the same software code base. It's sort of the same problem as we have in GSM. There's a couple of firmwares which are signed, and they run on all phones or on most of the phones. In IoT, we have the same thing. We have a common code base with similar vulnerabilities. So one specific version of a system is hacked, it scales to lots of different devices, and that makes them equally vulnerable. And the functionality is then not really important anymore. It depends on the system and on the firmware itself. So citywide attacks can be realized without penetrating air-gapped systems or infected servers. So that makes things sort of more easy. Constraint device form the smart city of the future, like vulnerable light bulbs or spreading malware across a smart city. There were some estimations how much of these small devices actually needed to protect down a city like Paris that was set to around 15,000 random locally located light bulbs should be sufficient. Like one example is the Devil's Ivy vulnerability, which was published, I think, so 5 months ago. So smart things to improve over time. So not really. So there are yearly security reports on Hewlett Packard, which basically buy available IoT devices and make a security evaluation. And you basically, if we can, every year we can look at the report and we end up with basically all devices being more or less vulnerable. Here we look at specific different kind of attacks or security tests of different devices, and we end up with 9 devices primed for this, or 6 out of 10 devices are vulnerable to this. So we could check this for every year, and things basically do not improve. It just stays the same. Vulnerabilities are not fixed. New vulnerabilities can come up, and they're not fixed neither. So at some point, all devices will all be vulnerable. So here we have the report 2016. It does not really change. So now, okay, I will do the bonus slides at the end because they are quite a lot, and I come up to some conclusions. The thing is, there are numerous security challenges in IoT, and most challenges are sort of well known. So the constrained resources sort of magnifies them, so it gets more difficult, but it's not impossible to solve them. Smart cities provide a vast area of attack because IoT is highly vulnerable, they're very hard to fix, devices will run long time, and there are little resources actually to maintain that infrastructure. So technical and cryptographic solutions exist, so if there would be enough will, we could fix that. There are just a few open problems which could be specifically addressed, like key management, for example, is a problem. Trust gets an increasing problem. You need to put trust in some part of infrastructure, and since that was misused over a long run, that's a real issue. You have data minimization. You need sort of enforce companies to keep as little data as possible, but this contradicts business models in many cases. And usability is also an issue. So if you have devices, but you cannot really maintain them yourself, if the vendor doesn't exist anymore, then there are issues. If you cannot buy someone who actually finds the devices and fixes them. So other problems are that business models are via security and privacy. Then we have government paranoia via privacy protection, and we have various legal issues mainly related to intellectual property on one hand, on the other side freedom and privacy protection. So my final remarks before I go to the bonus slides. So if you care about your data, the point is be highly suspicious about everything labeled smart or cloud. So my opinion or my conclusion out of working in the IoT and smart city domain is it cannot be secured under current conditions. So if there's a smart service, if there's a cloud service, and you care about your personal data, don't put it there. Then the second question, will privacy and security in IoT and smart city get fixed at some point? I don't think so. So if this will happen at some point in time, then it means there will be a major disruption. There will be some sort of catastrophe which will change thinking of people, thinking of governments, and change of business models in companies. But will be problematic. And what about the cybercrime issue? I'm pretty certain it will come down hard. It will come down very hard. Infrastructure is not secure. I'm pretty sure that countries can attack each other already now. It will happen at some point. That will be pretty dirty. It's sort of a Cold War situation where there are a lot of opportunities between countries to bring down other countries' infrastructure, but at the moment it does not really happen on the large scale. So, how much time do we have left?
5 minutes.
Okay. So now I have the bonus slides. So these were attack scenarios we were looking at. They are all backed up with publications where there was at least one physical setup found where that kind of attack worked. So if we have street lightning, where we can large-scale black up whole city areas. We have ICT systems and public services, where retrieval and manipulation of sensitive information is highly critical, where our documenting non-existing events or sending task forces to wrong places. So ICT system and public services are in most countries not really secured at all. Here we have an intelligent lamp example. So basically all smart LED light bulb systems you have at the moment have some sort of vulnerabilities. So here in this case, we had a device which leaks Wi-Fi passwords. They need to be configured in, but it can be read out of the device. So then we have that hack of Google's Nest that's already, I think, 2 years ago. So then we have monitoring systems. So we have false reports which can be injected in these kind of systems, or we have the suppression of emergency messages which concern police and fire departments, or fiddling around with environmental monitoring. He already gave the example of the city of Tarragona, where we set up infrastructure, but where consequences of false alarms are pretty critical, and that will happen at some point in time. Some more attack scenarios: we have cameras, like the distributed denial of service attacks using cameras that already happened a couple of times. So here I have two examples of DOS attacks, but I think we had a conference talk on this already, so I will skip this. So smart meters, I already mentioned that we have a couple of cities, a couple of countries which actually enforce smart meter infrastructure or give benefits on this. These devices are vulnerable, and these devices are not secureable anymore. And problem is that many companies build services around smart meter infrastructure, and there are privacy regulations coming up in some countries which will enforce these service providers actually to implement security which is not possible on these devices. So that sort of will contradict, and these smart meters devices will run for 15 years with security consideration looking forward for 2 years and do not work already at that point in time. So there are some serious problems coming up there. So smart grid. Okay, that's like frequent measurements reveal detailed information on household activities, including presence, electrical devices in use, and even what content consumers watch on television. So that's also smart meter context. So let's see this. More attack scenarios. Traffic control systems, that's a pretty interesting thing. Traffic control, they could cause traffic jams and accidents. We have the manipulation of traffic light status and traffic guidance systems. Falsification of traffic information. We can exploit confidential information out of these kind of systems. like also looking at emergency services, and there are also other control systems in similar infrastructure like railways, which are also hackable at some point. There was one example of a student, of a school kid actually playing around with a remote control at a traffic line and he figured out actually to change the traffic, like the light status on the train line using a remote control. It's all technology. You have remote controls which adjust to different frequencies or infrared signals, and where he was able to change this as a school kid, which could have had dramatic consequences if we would not have lived at that point in time. But that's all the infrastructure. So if we look at recent infrastructure, and then in 10 or 20 years in the future, we will have similar issues. So, okay, that's a traffic light thing in the United States. That's also pretty interesting. US traffic control systems, US intersections are vulnerable. So there are three major, like traffic control systems. It's basically, if there's a police car coming or emergency car, they can set the traffic lights green. So we have lack of communication encryption on the network level, so replay attacks work. We have a lack of secure authentication at the system level, so we have default usernames and passwords, and you can connect them basically. We have currently around 100,000 intersections in the US and Canada, which are vulnerable in this regard. And there was a publication 2 years ago which recommended defenses on organizational and technical level actually to fix this. Until today, nothing really happened. It was the University of Michigan who really found this out. And and we have similar situations in other countries as well. So these systems were considered secure like 10 years ago, but aren't anymore. But these systems will also keep on working for another 10 or 20 years. And that was not taken into consideration, and we do the same mistakes again. So I have a couple of more attack scenarios related to waste management systems, which were already broken, where you can change the garbage container filling level information and by this manipulate how the garbage collector cars are programmed for the day. So you can cause traffic jam by this or do other funny things. You have water management systems where you can manipulate the water quality, where basically if I would be some chemical factory or some atomic plant where I know that water quality can be affected at some point, I would have tools ready to manipulate a running system just to make sure that in case something gets wrong, this will not get detected, and it will detect it maybe 50 years when there are health consequences, but it cannot be mapped to me because there's no record. So, and these systems are vulnerable. Then we have location-based services. Okay, that was previously discussed. Most detail what the weaknesses are of these kind of systems. So, and then we had our conclusions. Okay, thank you very much. Thank you for listening.